Welcome to your next video on angles. Now, before we can really talk about angles, angles are made of things called rays. And rays are kind of like a hybrid cross between a line and a segment, two things that we have previously talked about. So a ray, by definition, has one end point where it cuts off, or maybe you can think of it as a beginning or an ending, and extends infinitely in the other direction. So it has an end point like a segment, but it extends infinitely in the other direction like a line. Okay, so it's kind of a segment, it's kind of a line, but it's called a ray. And so what's it look like? It could look like this. So point G, this is kind of like the segment look to it. Point H and the arrow cap over here looks more like what we would associate with a line, right? So, and I'll unhide this here in a second. If I just showed you this much, you would maybe go, oh, well, this is looking like a segment. But if I showed you the other half, and you would go, oh, this is looking like a line. Well, if you see both of those things, it's a ray. So how do we write it mathematically? Well, this is where it gets a little bit different, because in the past, with lines and segments, it didn't matter the order that you wrote the 2 points in, right? Like if that had been segment GH. So here, let me hide the arrow cap. Let's say this was segment GH, all right? And we could say this was segment GH or segment HG. It didn't matter if we went G to H or H to G. But for a ray, it will matter. It will matter. And so when naming a ray, the end point, in this case G, must be the first point. So we could not name this ray HG, because that is saying that H is the end point and G is where it runs off to infinity and beyond with Buzz Lightyear. But it doesn't here, okay? So that'd be funny. I need a little Buzz Lightyear character where it goes off to infinity. So the other thing is we're going to have our 2 letters, and again, that first letter, that G, that must be always the end point. That must be the end point. But the little baby ray, sorry, this isn't barbecue sauce, but this little baby ray that's up above our 2 letters, it always points to the right. Even if the ray, let's say I had a ray that looked like this. Okay, let's say this was ray GH. And so I would still name it just like this. Okay, so even though it's going in the wrong direction of going right, the little baby ray symbol always points to the right. All right, first example, name as many unique rays as possible. All right, so I will tell you there are multiple answers to this, and some people might be questioning and saying, well, clearly there's only one ray here. And so you got to keep in mind, how long is a ray? Well, a ray's technically infinite long, right? It has a starting point. You could put a ruler on an end point, but then it just runs off to infinity. So you may have different starting points, right? So I will say, what if we had just ray ZX? Okay, could I call this diagram ray ZX? And I can, because there's an endpoint at Z, and it goes off to X, and notice beyond X it continues on to infinity. Yes, it does go through points C and V towards infinity, but that's okay. Remember, there are infinitely many points, technically, on this ray, just like there were infinitely many points on a line, and technically infinitely many points on a segment. Now, could I call this in a unique way, a different ray ZC? Well, technically, ray ZC is the same as ray ZX, because it starts at Z and it goes towards point C and to infinity and beyond, which is the same thing as ray ZV. So these are all the same ray, technically. And again, I'm not going to say this is always going to apply here, but you're really looking for that endpoint to know if it's really going to be the same or not. And it's not always going to be in that case, because I could have multiple rays in this picture, and then that's not something that would necessarily be true. So these are all technically the same. They're not unique to each other. So I'm just going to cross these 2 off. This was my first real unique ray. Now, who says that I have to start at point Z? Because I could start my ray at point X. X is a point, right? I'm just going to ignore what happens before it. And so I could call this ray XC. Or, instead of C, I could say V. That's a bad looking V there. Let's try it. There we go. So start at X, go towards C to infinity and beyond, or start at X and go towards V, which is in the same direction as C. So again, this is kind of a duplicate of this. So there's two unique rays we have there. But once again, who says that I have to start at Z or X? Couldn't I start at C? And this could be my ray. So I could start at C, go towards V to infinity and beyond. And notice there are no other defined points, towards V. So there's really nothing else I could confuse that with. Now the question boils down to, what if I ignored C and I started at V? What if V was my endpoint? Is that possible to now name a ray? And do I have a point defined between my endpoint and my infinity and beyond? And there is nothing defined here. So I can't have ray V question mark. That's not going to cut it there. And you can't just name a ray with one point. You can't just say V and then put a baby ray above it, because that doesn't work. You need 2 points. You need an endpoint, and you need a point that it's going towards infinity and beyond. So in the end, how many unique rays are there? Really, 3. So now we get to talk about angles, because angles are made up of rays. So an angle, by definition, consists of 2 rays that have the same endpoint. Okay, so notice in this picture we have ray AC. Here's A, and it goes up to C, and then to infinity and beyond. And then we have ray A, starts at A, goes towards B, and then to infinity and beyond. So notice in this case, AC, ray AC and ray AB, even though that they both use A, AC and AB aren't the same ray because they're going in different directions to infinity and beyond. Okay? So they are unique rays because they're not collinear with one another. All right, the end point of our 2 rays is called the vertex. And this is a vocabulary word we are definitely going to use quite a bit throughout the year. So point A is our vertex of our angle. You can also think of the vertex like the elbow of the angle. Imagine this angle is like an arm, and the vertex is your pivot. Your elbow is how I kind of think of it. And the rays are the sides of the angle. So again, ray AC is a side, and ray AB is a side. So how do we write an angle mathematically? Ooh, this one's going to be fun because there are some variations to this. First and foremost, we need the angle symbol, which really just looks like a little small angle, right? I mean, we had a little baby ray, not barbecue sauce, guys. But we have a little baby angle, and then it's going to take 3 letters or 3 points after the symbol. But there is an exception to that. There's actually 2 exceptions to that. We could use the vertex letter instead of 3 points, or sometimes there might be a number instead of a letter present. So in this picture, we could name this, and we'll start with the exceptions, if you will. This says we could just use the vertex letter. Well, which letter was the vertex letter? Well, the vertex letter was A. So I could call this angle, so draw a little baby angle, A. So this is our first symbol that's not on top of the letters. This is really going to be, to the left of our letters or numbers here. So this could be letter A. Or I said if there is a number present, like this 1, and this isn't a 1 degree angle, notice there is no little degree symbol up here by the 1, but if you see a number present there, then we could just call this angle 1. Now, your safe bet, and this will apply to more circumstances than just these two circumstances of using a single letter or a single number, because the numbers aren't always going to be there. And I'll show you some scenarios where you cannot just use a single letter. But if you use the three-letter approach, I say right here that if you use the three letters, the middle letter must be the vertex, and that is our A. So what we do is we use our to infinity and beyond points on our sides of our angle. So I could call this, I could start with, let's say, C. Then I got to get my middle letter. It's going down to A. So C, A, and then I go to my other infinity and beyond point. So I could call this angle CAB, but angles, just like segments and lines, can be named forwards or backwards. So I could have started at B, went towards vertex A, and then went towards point C to infinity and beyond. So this one angle has the potential to have four different names that all represent the same angle. So again, these are going to be your fair bets, what I'll say. You're going to see this probably more common. You're almost guaranteed to always name an angle with three letters. These will be less common, but they're easier to do. All right, so our second example here. How many different angles exist in this picture? And at first glance, some of you might just say two, right? You'll go, hey, there's this angle that's right here. I see that. And I see this angle that's right here. There's two angles, that's all. Two angles. And some of you might be going, no. What about the great big one? And some of you go, great big one? Yeah. What about this angle? What about the overall thing that has the two smaller angles inside of it? That's a bigger angle, right? So there's really three different angles that exist in this picture. And then I say name each of those angles in as many ways as possible. All right, so we're gonna do some color coding here to be able to differentiate between our three different angles. So let's start with this small angle right here. All right. Now notice there are no numbers in here. There's not like angle 1, angle 2, angle 3. So that goes out the window. And this is where the other exception. Let me just jump back here. Like angle A. Can I just call this angle Q? And we're not going to be able to just call this angle Q. And why can't we call it angle Q? Because vertex Q belongs to multiple angles. So if I said angle Q, am I talking about this angle? Or am I talking about this angle? Or am I talking about the big angle Q? So if there's ever any debate of using a single letter, and if you say, hey, angle Q, and I'll go, which angle Q? Which one? And if you have to then describe to me more fully which angle it is, that means you're going to have to use the three-letter format. So this angle, let me write with green to match my green here. We could start with P. We could go to the vertex Q, the middle letter, and we could go to S. Or we can do it backwards. We could have started at S, went to Q, went to P. But then that's it for that angle. Okay, we can only use the three-letter formats on this one. What about, let's do blue here, this other smaller angle? So for this one, we could start at S, go towards Q, and end at R, go S, Q, R, or backwards, R, Q, S. But again, can I call this angle Q? And again, I run into that same situation of, well, which angle Q? Because there's technically three angle Qs. And then, let's see, what should we end with here? Let's go red. Let's talk about the great big angle. Let me get red. So we could start at P, go down to Q, end up at R, angle PQR, or flip it around backwards and go RQP. And again, I cannot call it angle Q because am I talking about the big angle Q or the top small angle Q or the bottom small angle Q? So there is really hopefully a good example of when it's acceptable and not acceptable to use the single letter for the vertex. In this case, it's not possible. But if there's just one single angle present, then sure, you could call it by just that vertex letter. All right, some little pieces of information in here. The measure of an angle is written in units called degrees. You guys know that angles are in degrees, but there are other ways to measure angles, which you'll get into more in pre-calc. Okay, so don't worry about that. We're just going to stick with good old degrees. And the measure of an angle in your book will be denoted with a little lowercase m in front of the angle symbol. Okay, so what I mean by that is if I had a 90-degree angle, okay, so let's say something's a 90-degree angle, and let's say angle A, for instance, okay? So if I had angle A and it's equal to 90, in your textbook, sometimes you'll see an m in front of the angle symbol. And all this is really saying is the measure of angle A equals 90 degrees. So don't let that m fool you. Over the years, I've had students think that that's a variable that they have to solve for. And again, that just means measure means you're going to be talking about a specific value. Okay? Now, if you leave out that m, to me, it's not the end of the world. If you just said angle A equals 90, okay, I'm okay with that. All right? But technically, you should put an m in front of there. You're not going to see me really do that a whole lot. So don't worry about it. I just do that because in the book, they put the m in there. There we go. So two angles are congruent angles. We talked about congruent segments in some previous videos. So angles are congruent if they have the same measure. So in this diagram below, the two angles have the same measure. So angle DEF is congruent to angle PQR. And so just like we did with segments, we could use that congruent symbol. It looked like an equal symbol with a little squiggle or a tilde on top. But you know, both of these angles, and let's just say, I'm going to estimate here, I don't know, let's say they're 135 degrees each. And since they have the same measure, then we can say that they are congruent to each other. And remember, when we use the congruent symbol, we really aren't talking about a specific numerical value, even if they may have a specific numerical value. So angles can be equal, they can be congruent, and it really represents the same idea of equalness. All right, if angles are equal in a diagram, remember with segments, we had special symbols. So let me just refresh your memory there. So let's say we had this segment, and let's say we had this segment. And if I said, hey, those two segments are congruent to each other, then we put these little markings like that on there. And that told us, hey, those segments are the same. They're congruent to each other. Well, angles also have markings that can show equality. So I've got two separate examples here. So let me just kind of hide that other example temporarily. And so if I wanted to say that this little angle and this little angle were equal to each other, then we're going to use what I like to call arc marks. Little arc marks. So little curved arc. So you're going to put one on this angle, and we're also going to put a matching one over here on this angle. Now notice I didn't kind of make them right next to each other. Notice I made a little separation in here. And the only reason why I do that is because if you do this arc mark and then this arc mark, that kind of looks like to me one big arc mark. And maybe you're saying this angle is going to be the same as some other angle that you maybe haven't drawn yet. Okay? So when I draw in two arc marks that are right next to each other, I'll have one here, and then maybe I'll put one out more so like that. Or we could do it the opposite way, right? I could have one arc mark right here, and then another one right here. So that distance away from the vertex really has no meaning to it. Okay, we're just looking at the number of markings. So now let me show you this example. If I wanted to say now that this angle and this angle, so don't mark anything yet, I'm just trying to illustrate what's going to happen here. I want to say these two angles are equal, and I want to say that these two angles are equal, but these two angles aren't the same as those two angles. Now, how do I mark that? Okay, so now let me hide that other example over here. So maybe, again, I want to say, and maybe this is a fresh set problem. There's no markings that have already been used, so I'm going to go ahead and use the single arc mark and a single arc mark. So here I'm saying these two angles are the same. But again, these two angles are the same, but not the same as those two. Well, since these two angles use single markings, well, now I'm just going to use double markings on these other two angles. So I'll put two arc marks on one angle. And then, again, I'm going to kind of make these not flow all together here, but then these two angles. So these two over here are the same, and these two over here are the same, but not all four angles are the same. Now, could you do 3 arc marks? Could you do 4 arc marks and 5 arc marks? Yeah, that's really, you just add another set of markings if you want to show that another set of angles are the same. Is it possible that you could use, I mean, let's say, for instance, that all 4 of these angles are the same. Could you put single arc marks on all 4 of these like this? Yeah, you could do that. So it doesn't just have to be 2 angles could be the same. Maybe 3 angles are the same, and they all use the same marking. All right, next up, our angle addition postulate. And you might remember we had something called the segment addition postulate back in the day that really just said a little segment plus another little segment equals a bigger segment. And so now we get to do the same thing with angles. We're going to have a little angle plus another little angle, and then when you put them together, you get a bigger angle. So this says if point B, here's point B, is in the interior of angle AOC, and here's angle AOC, so it's in the interior, it's kind of inside it, then what we can do is we can take that big angle AOC and we can draw another ray OB, to split it up into 2 smaller angles. So the angle addition postulate is saying we got angle AOB, there's angle AOB, plus angle BOC, this other small angle. And what happens when you take a little angle and another little angle and you add them together? You get this entire big angle. So segment addition, angle addition, same idea, just 2 different things. We're dealing with segments or we're dealing with angles. Now, I'm also going to throw in another vocabulary term before we start to apply the angle addition postulate. And sometimes we may want to cut an angle in half. We may want to what's called bisect the angle. And we used the term bisect before in a way that also described a midpoint. So let's say I had a segment and I had the midpoint right here. This was the midpoint. And I know it could be the midpoint if I saw some additional markings, right? We said if this segment was the same as this segment, if they were congruent to each other, then yes, this must be the middle point. Well, the midpoint is also really bisecting the segment in half. It's cutting it into 2 equal parts. Well, we can have rays that cut a big angle into 2 smaller equal-sized angles. Okay, so if this was a ray, I guess I need to get my arrow caps on here. Where'd my arrow caps go? So let's say this blue angle is our big angle, and this red ray is an angle bisector. Then what happens is we know that this little angle up top and this little angle on the bottom are going to be congruent. Okay, so if we have an angle bisector present, then boom, we get 2 matching angles. All right, so in the diagram, ray YW is an angle bisector of which angle? Well, it's cutting in half this bigger angle, XYZ. Angle XYZ. And I know that ray YW is an angle bisector because, and this is the part that's not on your notes here, but these markings here, these arc marks, these are saying, hey, if these 2 smaller angles are really equal to each other, then hey, this YW must have caused that bisection to happen. So these markings are telling me that these 2 smaller angles are the same. All right, so now to some examples with these. So if the measure of angle BDA, let's find, where is BDA? So here's B, here's D, here's A. So BDA, we're really talking about this smaller angle that's on top. So it's equal to 37 degrees. So what I might do is this. I'll put in 37 degrees kind of right inside the angle. And the measure of angle CDA, well, where's angle CDA? CDA, oh, it's the great big angle. So what I might do to show that is this. I might use some like curly brackets here and say all of this big angle. That's 64 degrees. Then what is the measure of angle BDC? Okay, so where's BDC? BDC. Oh, it's this smaller angle that's on the bottom. Okay, so that's the angle I want to know. So you could think of this as like X, if you will. Now, some of you might look at this and go, this seems pretty easy, right? If I've got a little angle and another little angle, and together I know that they need to add up to be this bigger angle, well, instead of doing the angle addition postulate, it's kind of like you're doing the angle subtraction postulate, right? You know what the final answer is, and you know how much one part is, so if you take the difference, you can get the other part. So we could set this up with the angle addition postulate and say when you add up these two small angles, we should get an overall answer of 64. So if I subtract the 37 degrees over to the 64, then we end up with 27. So this angle is 27 degrees. All right. Now I have a secondary question here. Is ray BD, no, not BD, DB, ray DB, is ray DB an angle bisector of angle ADC? Is DB, ray DB, cutting this 64 degree angle in half? And this is where you want to look at your values. Are these two smaller angles the same value? No, they're not. So is ray DB an angle bisector? No, because the smaller angles, and sometimes instead of writing out the word angles, commonly I'll do a little baby angle, apostrophe S. The smaller angles are not congruent. And again, instead of writing out the word congruent, I'll put the symbol for congruent. Now, if you wanted to specify what the smaller angles were really referencing, you could say angle ADB and angle CDB. Those are the smaller angles specifically. If they were the same, then yes, ray DB is an angle bisector of angle ADC. All right, the last example we're going to do together, and it's kind of a two-parter. We're going to do the first part. I'm going to leave the second part for you. So it says draw angle KAH so that ray AN is an angle bisector of it. Use appropriate markings to illustrate that angle KAH truly is being bisected. So I need to draw an angle. An angle is made up of two rays. So it really doesn't matter how you start this off here. So we'll say here's one ray, which means this is the vertex. This is going to be the endpoint. But I need another ray that uses the same endpoint. Doesn't matter how big or small it is. It doesn't. So let's say, and if it's KAH, remember that middle letter A is the vertex. So we know this has to be A. Does it matter which, and we get to put some points towards the end here. Does it matter which one's K and which one's H? It doesn't matter. Let's just do that. So there's angle KAH, so that ray AN is an angle bisector of it. So we're going to bisect this angle into two smaller congruent angles. So I need another ray, and it's got to, remember, it's got to start at A, it's got to start at the vertex here, and it goes off in this direction. And we're going to make it look like it's relative, if I can say my words right, relative, I can't even think of a word I'm trying to say. We want to make it look like it's plausible. So I'm just going to put it like off in here. There's a ray now. I need to put in somewhere along this ray. And there's ray AN. Now, it says use appropriate markings to illustrate that this really is being bisected, which means these two smaller angles in here have to be the same. So I would put an arc mark on one angle and then another single arc mark on the other. Okay, so there's kind of this setup. There's a good picture for you, but your picture could look slightly different as long as basically you're bisecting your angle. Now, what I want you to try is to now take this picture and apply this information to it. And there's one more example I want you to look at, and this is where it starts to get pretty intense looking algebraically. And I show two separate methods for solving this problem. One of these methods is correct, and one of them is incorrect. And I want you to be able to, in the end, explain which method is the wrong way of doing this. All right? So good luck with those last two problems there.